Okay, welcome back to a new math tutorial. In this video, I would like to explain a few things related to the so-called golden ratio. Especially when you study something related to math, any kind of science subject, you might listen to a lecture called analysis. And there, this is a really interesting topic which normally occurs in the beginning of the lecture. Yeah, where you have to do some calculations with this so-called golden ratio. Sometimes it's also called golden cut. And the definition is very simple. Yeah? If you have a length of a line given as a plus b, and you divide this line into certain fractions a and b, then this so-called golden ratio, which is normally denoted with tau or with phi, these two Greek letters, yeah, then this golden ratio is defined as this equation here, a over b equals a plus b over a. And when you solve this equation for a, you find out that you get an irrational relation between a and b. Yeah, so this is here in this case 1.618, but these are only the first digits of an infinite amount of digits. Yeah, it's a real number that comes out, yeah, which you cannot represent as a fraction of two natural numbers, for example. And this I found very interesting in the beginning, because when I saw this equation for the first time, I was not expecting that this turns out like that. Okay. And then here we want to concentrate a little bit on the practical meaning. So as you might know, you can also find this in the internet. Many websites are showing that in human history, many buildings have been produced in a way that they obey this so-called golden ratio. And one of the examples which I want to calculate now is the so-called Eiffel Tower in Paris, which has a height of 311 meters. And the distance between the middle platform and the ground level is 116 meters. And now we want to check whether this ratio, which we obtain from this, obeys the golden ratio. And if not, then what is the deviation between these two? So now we can directly, as usual, dive into the topic. And what I would like to do is say a few words about the so-called golden ratio. And for that purpose, I would like to draw a line here. Maybe I can do it like that. And this line should have a beginning, which could be, for example, here, and it has an end, which is somewhere here. And then we also divide this line into two segments, as I have said before. And the division, the position of our division, is actually the so-called golden ratio. And now we can define some length here. So maybe we can here say that this should be our length A, this should be our length B, and when we take the whole length of our line into account, then of course this must be A plus B. Okay, and now we can start our calculation. So this segment here divided by this segment is actually the full length of the line A plus B divided by this segment here. And and what we can do now, we can start our calculation in the following way. So first I would like to write down again this golden ratio, A over B, we said, and this has to be equal to A plus B divided by A. And before we start our calculation, I would simply set b equal to 1. As you will see later, this has no effect on the calculation itself, yeah, because at the end what we get out from that, we only have to multiply this with b again, and then our result is again okay. So now when we do this, it turns out that our relation gets a little bit easier to handle. So this is now a divided by b is equal to 1, so a remains, and this has to be a equal to a plus 1 divided by a. So now we have to solve this for a, yeah, in order to show that this relation here is true. So what we do, we multiply this whole equation with a, and this leads to a square equal a plus 1. Now until now it's quite simple. We have not done anything else except bring this a to the other side. And now what we can also do, we can subtract both sides with a to get this a to that side here, and then also subtract 1. And when we do this, we get our nice quadratic equation, a squared minus a minus 1 is equal to 0. So this is interesting because now we have a simple quadratic equation. If you replace a with x, then you can directly see it. And what you could, for example, now use is the PQ formula. Yeah. And if you want to practice this, you can go to my video where I've explained how to use the PQ formula and then try to solve this and see whether you get the same result as if we are getting now with the method which I'm using now in this video. Because in order to, I thought in order to practice this a little bit more, I would use now the method of completing the square. Yeah, this we have also used for deriving the PQ formula, but I think it's quite instructive to do it in such a way. So what we do, we have to find out if we take this as a first part of our binomial, second binomial formula, which is in this case a minus b squared would be a square minus 2ab plus b squared, and we identify this here with 2b, then we can see immediately that we have to add up the square of 1/2, which is 1/4. So when we do that, we can write here now a square minus a plus 1/4 minus 1, and then we have to, of course, also add 1/4 on the other side to make sure that our equation does not change its values. Yeah, so now we can directly here use our second binomial formula. So what we can write now is a minus 1/2 squared minus 1, this remains, and this has to be equal to 1/4, as I said before. So the only thing which we have to do now, we have to bring this 1 to the other side. So this is then a minus 1/2 squared equal to 1/4 plus 1. Then the only thing which we have to do, we have to calculate the square root, which gives at the end a minus 1/2, and this has to be equal to, of course, plus minus square root 1/4 plus 1. As I have explained in some videos already, you get, when you take the square root, you always get two solutions, which are plus minus. However, I would like to concentrate only on the positive one. The negative one does not make any sense in this case. So we can fully ignore that minus here below. So yeah, then in the next step, the only thing which we will do, we will bring this 1/2 to the other side. So we can write here plus 1/2, which means a is equal to the square root of 1/4 plus 1 plus 1/2. Yeah, then we can do a little bit more. I mean, this is already the solution, yeah, but we can already do some more simplification here. Yeah, we can easily replace 1 with 4/4 to bring both to this common denominator. So this means we have a equal to 1/4 plus 4/4 plus 1/2, and we can also bring this 1/2 in front. Though this is then, of course, a equal to 1/2 plus the square root of 1 plus 4 is 5, so this would be 5/4. So the next step which you can do, you can bring this to a form which you usually find in the literature. So what we can do is take the square root of 4, which means we get 1/2 plus square root of 5 divided by 2. Yeah, the square root of 4 is 2. And then we can bring this to a common denominator. Because we have already 2 here, we can write 1 plus square root of 5 divided by 2. Yeah, and this is the way how you can actually find it, as I said, in literature. And then this gives, when you calculate this, a value of 1.618. And yeah, this is our result for A. And now, as I said, because we set B equal to 1, we have to multiply this with B at the end. Yeah? So this would be 1.618 times B. So now we have our relation that we were searching for. Yeah? exactly this part here. So now we have proven that when we make this division of a line with the length a plus b in two segments a and b, and we define the position of this division with the help of this so-called golden ratio, what we get at the end is an irrational relation between a and b. And as I said, I still find this very interesting. So now what we do next, we will solve this problem with the Eiffel Tower. So this is actually part B. So what we can do, I can try to draw now the Eiffel Tower as good as possible. So this is the base. And then we have here another segment with a platform. So we have one lower platform here, we have one middle platform here, and then we can also increase this to the highest platform, which is somewhere here. So now what we have is the full length given of our Eiffel Tower, which is here. Now we choose another color, maybe red. This is 311 meter. And then what we also have is actually the distance here between the ground level and the middle platform. Yeah, and this is 116 meter. Yeah, and this is actually our B, and this is our A plus B. The full length. So this is the smaller part, and what is not known until now is our length A, but we also don't need this, as we will see in a few minutes. So now we can calculate our golden ratio. So let's call it again tau, which is as we have defined it before, A over B. And as I said, A is not known, but we know the full length. So this would be 311 minus 116 meter divided by B, and this is again our 116 meter. And if we calculate this, then we find out, we can do this with the help of a calculator, that this is 1.69. So the ratio between this one and this one is 1.69. And now in the next step, I would like to calculate the deviation, which we get between the value which we obtain here and the real golden ratio. So what we can do, we can write down our value 1.69 minus the real golden value, the real golden ratio value 1.618. 1.618 divided by 1.618, because we want to see how much far away we are from that. And when you calculate this, you come to a value of 4.4%. And this is quite interesting, because I think when you take all the measurement errors that you have into account, in addition to some construction failures and all that, 4.4% is actually a really good value, and it's very close to the real golden ratio. And as I said, you can find this for many buildings in the world, that you have certain ratios obeying this golden ratio. And I hope that you find this instructive. I hope that you learned something new. And if you like the video, I would be really happy if you hit the like button, if you subscribe my channel if you have not done so far, and then hopefully see you soon for a new video.